this is another type of switching loss which is called dead time switching loss. So you have these FETs. What would happen if I turn on them simultaneously? So this is, let's say, 50 milliohm. This guy is also 50 milliohm. So this is empty. So it's empty and MA turned on. What will be the IDD current? 500 milliohm. So if this is 1.8 volt, how much? 18 amps. Okay, and you have sized this to derive maybe 1 amp or 2 amp. So 10 times more current, it will break your power factor. Okay, it will damage your metals, it will damage your FETs, everything. So these we have reliability due to height. So we need to make sure both M and P are 17. So use non overlap completers. You can also go break before, which means you turn on the other switch, but you have to break the current switch before you turn on the other switch. So let me call it V of V gate. Okay, and this is generated from a single clock only. So we'll look at the circuit how it's generated, but you just assume you have a PWM coming from your feedback loop and you split into two non-overlap clocks. One becomes P gate, other becomes N gate. So this is your P gate, V of P gate. This is the time actually where both FETs are off. So your P gate is high, so that's a PMOS, so that is off, and N gate is low, so both FETs are off. And this is called TD, or I'll call it T dead actually. Both MN and okay. So when your P gate is high, the load current is flowing through PMOS. Sorry, P gate is low, your load current is flowing through PMOS. And if your N gate is high or bottom switch is on, your load current is flowing through NMOS. So now during this time, dead time, both are off. So where the current is going then? So this is your load current. So where will the current go? I mean, capacitor will start discharging, but what would happen to the inductor? And inductor other end is open, huh? No, high resistance is there, but think about all of a sudden you turned off both the switches. Inductor will maintain the current. Inductor is a current storage circuit, huh? Just like capacitor is a voltage storage. So there is a memory actually there in the inductor. The current of inductor cannot change instantaneously. It won't go to zero because it has some slope, RC time constant. So it will rise and fall based on the voltage. So if you leave that high impedance, the other node of your or VSW, if I call it VSW, and the current is still flowing into this. I mean, load current is, let's say, 1 amp. Okay, that was which was flowing through NMOS, and you turned it off. You leave it high C. That 1 amp will keep flowing for a certain time, unless the voltage across the inductor falls to zero. Current cannot be zero, So that where that voltage will go? It will start going to negative. And if it goes below negative voltage, then the rating of these devices, it may even damage your device. So this cannot go, or you should not allow this go to large negative voltage, otherwise it may damage your device. No, it will flow through the diode. There is a diode here, hidden diode, body diode. I'll show you. So this is your substrate, P substrate, correct? This is your N plus body. So if I call it source, this is nothing but, and this is your bulb. So what is diode? This is your diode, So wherever P-type diffusion and N-type diffusion meets, that will form a diode. So how many diodes you have here? change the color. So this will form N side and substrate will form P side. Another diode you have here. Okay, which means I want to draw here those diodes. Okay. So your P is common to both diode, which is a substrate, which is your bulk or body of the. So this is called body diode actually, and in most of the cases the body is tied to the, for NMOS, tied to the lowest voltage for because the P type, because you don't want to forward bias the diodes, and for PMOS it's tied to the highest voltage because body is N type there, and source diffusions are source and drain diffusions are P type. So if you connect to the ground, so the bottom diode will go away. Okay, the diode between bulk and source will go away if you short bulk to the ground and source is also grounded. So your diode left is bulk and drain. So what you have here, so this is tied to ground, you will get a diode here. Correct. So now if I have this yeah, but that will not conduct. So this will only go to negative. So the PMOS will have a P here. So that will always be reverse bias. That will not conduct. Because current direction is going from this to towards load. So this will always be negative then during that time. Okay. So that diode will not conduct. So this is VSW. So first let's see what would happen to the VSW. So what would be the VSW at this? So if this is VSW, where will it go? So this is going negative. IL, current is flowing in this direction. During that time, current will keep flowing. This will go negative. So the moment it goes below forward voltage, this diode will conduct minus 0.7. So it will get clamped at 0.7. So let's say this, and this will remain for the duration of. Now after this, what is happening? I am turning on NMOS where will it go? So if this is minus 0.7, where will it go when the NMOS turns on? So let's forget about the IR loss, IR drop. And you can ignore that. So it should go to the ground level, 0. So this is your 0. And it should remain 0 until this point. And we'll again do the same thing. Now what is happening after this? Which device is turning on? PMOS is turning on, so it should go to VDD. Correct? Then same thing. Okay. So how the current, inductor current will look like? How the inductor current will look like? So the slope will change for a very short duration. Otherwise, the slope will follow the same V in minus V out over L, and for negative slope, it will be minus V out over L. So because what is happening here, VSW, you are applying more voltage here. Instead of 0, you are applying minus 0.7 here, and V out remains same. So the inductor will see a larger voltage difference. So the slope will be steeper here. So let's say the inductor current was falling during this time. So before this, you assume that that was on. So it will hit the peak here, inductor current. Correct? What will happen here? You will see a so usually expect 0, but it won't be 0. So there will be a sharp change, and then it will start following the normal flow. Correct? And then what would happen here? So NMOS was on. So it will first fall and then and again same thing will happen. Okay, and this you can calculate from the slope. That's not difficult. This slope or this, what are the peak value of this extra you get, that can be calculated. Even though that would be negligible, but the shape will slightly change. So now, if I assume that this ripple is very small compared to the load current, then all these glitches and everything can be neglected. So if I want to calculate, so if ripple current compared to high load, then what will be the PDET? PDET switching loss. What will be that? What is the voltage? Voltage is VF, forward voltage of the diode. Okay. Minus VF and multiplied by current. How much current is flowing? How much current flowing in the diode? Load current, and if so this is your peak power, but this is not happening throughout the entire clock period. So you have to take the average of that. So this is only happening for TDED divided by TSW, and this is happening twice. It's happening at both the edges, positive and negative. So multiplied by 2. So approximately twice of VF Now let's take an example. So let's say I load is VF equal to 0.7 volt, I load equal to 1 amp, TSW is 1 microsecond, and I'll keep, let's say, TDED 10 minutes, which is 1% of your TDED. Okay. Two into 0.7 into 1 into which is so much 1.4 divided by 100. How much? So 1400 milli divided by 14 milliwatt. Okay, correct, which is quite huge, So at 1 amp 14 milli, sorry, if you are delivering, let's say, 1 watt power, how much efficiency loss you will get? 10 milliwatt is 1%, 1.4%. So 1.4% is not small actually. Okay, when you are competing with the different parts or different competitors, even you try to extract even less than 1% efficiency of that. Okay, so ideally I would like to have minimize this as much as possible. So what can I do to minimize this? It is the TDED. So if you make TDED equal to 1 nanosecond, then 1.4 milliwatt 10 times. So we should minimize TDED. And since this is function of load current, so at light load it will be negligible, but at mid and high load this may be significant enough to reduce your efficiency. So ideally we should try to keep it as low as possible, but we cannot keep it 0, obviously. Okay, so and because at any instead we should not allow the two FETs conduct simultaneously. So we have to have some dead time, but we have to minimize it. And since this dead time may vary across your process voltage and temperature, so we always look at the worst case actually. So let's say for worst case you design at 1 nanosecond. At the other cases, uh, it may reduce actually. So let's say you are going at a fast corner, then your delays will reduce. So that 1 nanosecond may further shrink. It may go to half a nanosecond also. So across all the corner, you have to make sure that those two FETs should not conduct simultaneously. If you ensure that across PVT, then you always try to keep it as low as possible. And there are some adaptive this dead time circuits also, where they keep track of that dead time and will keep changing the delay and in your non-overlap clock generator to ensure a fixed time. So let's say you are happy with 100 picosecond, and if you maintain that 100 picosecond across all PVT, which ensures that your power FETs will not turn on simultaneously, then that will always log that dead time at 100. So that can be done using a like a DLL kind of a circuit, or there are some other circuits also. We'll talk about that later when we look at the different techniques to improve the efficiency.